Memories bring back your. There's a time that I remember when I never and I fell out of the air. Everybody else. Memories bring back your. Yeah, yeah.
was the first day of school?
Fine, I guess.
Did you guys pick up on that?
Sure did.
Something's wrong. Signal the husband.
Uh-oh, she's looking at us. What did she say?
Oh, sorry, sir. No one was listening.
Is it garbage night? We left the toilet seat up. What is it, woman? What?
I'm joy. This is sadness. That's anger.
What?
This is disgust. And that's fear. We're Riley's emotions. These are Riley's memories. They're mostly happy, you'll notice, not to brag.
I wanted to maybe hold one.
What happened? Sadness?
She did something to the memory.
Is everything okay?
I don't know.
Take it back, Joy.
Trying. Joy, no,
Let
wait.
go!
The core memories.
Can I say that curse word now?
What do we do now?
Nothing's working. Why isn't it working?
We have a major problem.
Oh, I wish Joy was here.
We can fix this. We just have to get back to headquarters.
That's long-term memory. You could get lost in there.
Think positive.
Okay, I'm positive you will get lost in there.
Well, so good morning, everyone. Welcome to CS203 again. So you guys probably know that we just played a video clip on Inside Out, and if you haven't watched the movie of Inside Out, Disney Plus is probably the best place you can find it. And so I guess a lot of you probably already watched that movie before, and it's actually a pretty good movie from my perspective. It's actually one of my favorite Disney movie. Well, most of the time we consider Inside Out is talking about a girl's social scene and how do you manage your I would say like emotions. However, from my perspective, from the computer scientist's perspective, I would imagine that this is a very good movie talking about memory. And also we before the movie clip, we also played a song called Memory. So it's probably not too difficult for you to imagine the topic that we are going to talk about today is mostly on memory. So, but before we start, it's always good to talk about, to put you on a big picture. So the big picture, again, computer architecture, von Neumann architecture is our big picture. And what's in von Neumann architecture is after you compile the program will consist of instructions and data. They are all in the encoding format that your machine can understand. And what's really in your machine, the main part consists of two parts, the processor and the memory. And whenever you want to run a program, you just load the instructions into the memories, and you also load your data into the memory. And whenever your processor wants to execute the instruction, we just fetch the instruction line by line and looking over what instruction want us to do. If the instruction want us to access data, then we access data. So in this way, it's not too difficult for you to imagine that, well, every time when your processor needs an instruction, it has to be from the memory. And when you need a data, it's also from the memory. So, and to evaluate the performance under this kind of architecture, because it depends on how many instructions in your program and how much time it takes to execute an instruction. So the execution time on the processor will be instruction count times cycles per instruction times cycle time. And we have a definition of speed up, which is the execution time of the old system over the execution time of the new system. And a programmer is the only one who can affect all factors in your system. And sometimes we care about performance because we want to compare, we want to gauge what is the best system that we should use for our applications. And sometimes if you are not careful about the metrics that people are using, you may be misled. So one of the good example is T-flops. So T-flops is a matrix that talking about how many tera floating point operations that this computer can execute. But if you look at the formula, it's actually missing one of the important factor in performance equation, which is instruction count. So in this way, T-flops is not a good metric that can help us to compare if I have a different instruction set architecture or a compiler, then what's the performance of different machines is about. And also, if your application doesn't care about floating point performance, this is also misleading. So here we got one thing that I want you to remember is that whenever we want to evaluate the performance, make sure that your performance metric must cover all aspects of the performance equation, that is instruction count, the cycle per instruction, and the cycle time. So in this way, you can imagine that inference per second is also not a good one because it didn't tell you how many operations per inference would take, and it also have no idea regarding the cycle time for these operations. And okay, so now we know we might have a problem in performance and what to address. So then a good thing, a good formula, or say a good law to learn is called MDOS law. So this slide gives you an overview of the MDOS law. So MDOS law is actually talking about like speed up is equal to 1/1 minus f plus f over s. And the f here is the fraction of the time of the target part that you want to optimize. And also its form is coming from the speed up equation. So it's probably not too difficult for you to even not knowing the MDOS law, but derive the same answer. However, what MDOS law is really important is its corollaries. So the first corollary is that if I want to evaluate the maximum speed up of apply an optimization on a certain part is 1/1 minus f. Again, the f is the execution time of that part. And also the second corollary is coming from the first one. If I have multiple parts that I can optimize, if I want to maximize my speed up, if I can only choose one, then the one with the biggest f value is the one that I want to optimize. And corollary 3. Right. If I have, well, you know, we are now in a post Moore's law era, and the performance gain is coming from parallelization, right? But what if I cannot parallelize anymore? So then the single core performance, does that matter? The answer is that it still matters, because if you look at the performance, the speed up we got is still determined by 1 minus f parallelizable, which is the single core part. So single core performance still matters, and that's why Intel and AMD, they are still important, even though people are talking about GPUs or other accelerators all the time. However, we know that, well, processors, CPUs, they are still important, but their improvement is now slowing down. So if you really want living in a world that you have a slow improvement on your processor cores, but you still want to improve your performance of the program, then explore more parallelism from a program is the key to performance. Again, from MDOS law, what it can tell you. So that's what we are at. And we were all talking about the processor part in terms of from the performance perspective. However, if you look at the two big components, processor and memory, then you will figure out that processor and memory has a huge gap in terms of their latency. By latency, I mean the time for us to fetch a single piece of data from the memory to the processor. So from the practice question I have in the last lecture, you know, since every instruction is coming from the memory, and because your memory is really slow, so even though I have a processor that can perfectly get everything done within just one cycle, but if my memory is this slow, then on average, each operation needs to take 69 cycles to be done, which means that your processor only accounts for less than 2% of the performance, but the rest of more than 98% of the performance is counting on the performance of your memory system. So according to Amdahl's law, if I really want to get performance, if I want to make architecture great again, if I want to unite for a better architecture, memory is the thing that we have to address first. So that's why we are going to talk about memory today, and this is the score, the standing of the each team. All right, so today we are going to give you some basic idea behind memory hierarchy, and we will tell you how cache works. Okay, so we just talked about that DRAM is slow. However, if you look at the look at the memory technologies that we are having, right? DRAM is the mainline memory architecture that we are using for now as a physical memory. However, above memory DRAM, there's another technology called SRAM. So the access time is only about 0.5 to 2.5 nanoseconds, right? And if you think about 0.5 nanosecond, that's about the same cycle time as your processor. So what that tells you is that if I can use SRAM as the backup memory, as the memory that my processor directly interact with, I can potentially get data as fast as my processor speed. But you know, there's no free lunch. So how expensive is that lunch? The thing is that in terms of a per unit cost, SRAM is about 50 times more expensive. So do you want your memory to be 50 times more expensive when you build a system? So probably not. So here is here is our here is our take. So we try to build, we try to use, here is our take. We try to use this small amount of expensive memory to build something called cache. And the idea is like this. So thinking about that, although I know most of you are not in this place right now, but if you remember the campus code UCR, there's a bell tower, right? And you know the tap water in California is not really drinkable. So, but the good water nearby UCR is pretty far away. That's called Arrowhead, Lake Arrowhead. It's a good place. You should visit if you have a chance when the pandemic is over, right? But you know, it's so far away to get the water. How far away is it? It would take you about an hour. So it's like, okay, so you can see that, right? If I want to drink the water, right? Do I really want to spend an hour every time to just get a cup of water, right? So instead, right, what we would do is that we just have some vending machine nearby, which potentially would have those, you know, water fountains nearby us. So it's like the analogy of our computer systems in a way that originally our processor would directly interact with the DRAM, which is about like 50 times more latency than access the processor core. However, if we can have some SRAMs inside your processor like this, then if we are lucky enough to get most of the data we need in the short term in the SRAM, then we only need to pay the overhead of access the SRAM. And this SRAM part in our architecture, we call it cache, C-A-C-H-E. And the pronunciation is very similar to, well, it's the same as cache. So that's why I just use the $ here in the rest of the lecture in case I don't have space for the word cache. Right, and you might, so water is one analogy, but you probably don't have a good idea why am I talking about water. So let's use another analogy I like more, that is the Inside Out. If you remember the Inside Out, and if you just watch the movie clips before the class begins, there are some terms they are using, right? So in the control centers, there are different emotions, and they would use core memories, which I would say is analogy to the registers in your processor. So whenever they want to deal with your memory, they would they would directly interact with the core memory, and there's no overhead when they are trying to access the core memory. However, if I want to have something more than just the core memory that I provide, look at the wall here. There are some short-term memory, or say the memory in the control standards, like the SRAM. So whenever they need something that's not in there, they just go to their shelves, and they will have the emotion that, or say the memories they need to make Riley happy, right? And then if there are something we cannot find here, you will see, like, they would joy and sadness, they just travel to part of their outside of the control standard, and that's the main memory, right? And if you really cannot find something from the DRAM, then it would take you the whole movie to the long-term memory to find stuff, right? So that's why I play Inside Out before the class, because it's really relevant, right? And if you don't know what I'm talking about, you probably should watch the movie. All right, so that's the memory hierarchy. Okay, so I have talked about the concept of memory hierarchy, but without having you practice a question, you probably won't feel how effective is the memory hierarchy. So now I am going to give you about 1 minute to 2 minutes to think about what's the answer of the question. Wrap up. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your initial vote, right now I don't see any answer surpass the 50% bar. So I think it's a good time for us to discuss with your friend. And again, sometimes the most popular answer might not be correct. So just make sure that you express your thought if you feel like your party, the rest of your party is not giving you a reasonable answer to convince you. So right now, just open the screenshot and start your discussion and we hope to finish the discussion within 2.5 minutes. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the discussion, I think, well, finally we got an answer that's over 50% as C, but there are still advocator of A and B. And you know, this is like the rest of the world. Sometimes the majority may not be right. So let's pick a team to tell you, to tell us what your team is thinking about. All right, so which team? Okay, number 2, Mystics. So who is the scriber of Mystics today? Can you raise your hand so I can pick you to chat with the rest of the class? Who is the scriber of Mystics today? Okay, Andrew. So what does your group think?
So we didn't have a consistent answer, but I choose C.
So what's the reason that you behind the answer C?
So for the memory part, I think same as the last question. So the CPI for the DRAM should be 26 divided by 1/2 gigahertz. So the
So it would be 2 gigahertz, then that will be, okay, so that will
56.
be like 52 cycles, right?
Oh yeah, 52, sorry.
Okay.
And for the cache should be 0.5 divided by 1/2 gigahertz.
0.2 divided by a point. Wait, say again.
0.5 divided by
Uh-huh.
1/2.
This is DRAM.
That's
And this is,
yeah.
so it's 0.5 divided by 1/2 gigahertz is also, so it's also 1, right?
Mm-hmm.
Okay.
And I think it says 90% of the memory access will be cached by the cache. So that's one cycle, I guess. So 90% times 0.9 times 1.
Mm-hmm.
And the rest of the 10% of the memory access will be DRAM. So 10% times 52. And I think also 30% of the instruction are load store instruction. So I think this extra memory access. So 30% times should be 52, right? Or yeah, something like that.
Something like that. But will that give you the answer of C?
Actually, I think 30% also need to times 0.1 because that's still 1%. I mean, 10% of it will be DRAM access, and the rest of 90% will be cache access.
Okay, all right. So let's go through this question again, right? So so first of all, right, if everything is perfect, right, in a memory, then the CPI is just 1, right? If everything is perfect, right? And so usually, right, if you just count the SRAM cache with the latency just at 0.5 nanosecond, you know it's aligned with your processor speed. And given that you learned the undergrad architecture that talks about you can pipeline things. So if it's just a cycle, and if this is a pipeline processor, usually we assume there's no overhead. And even though you add this one cycle, I don't think it would affect, if you think it's not pipelinable, and if you add additional one cycle, then I still don't think this would affect the answer significantly. But now let's just assume that you can pipeline it, so we don't add that as an additional overhead. So in this case, 90% of the time, we don't have to pay the additional overhead, or 90% of the time, like Andrew said, you just need to spend one cycle. But if you are not this 90%, right, which means that 10% of the time, you will have to still go to the main memory. And this part is the same as the last time, that every instruction and that's not in a cache has to go through the 52 52 cycle overhead. And 30% of the data access would also have to suffer from this 52 cycle overhead, right? But better than the previous case that everyone has to go through there now, because 90% is in the SRAM. So only 10% have to go there. And if you count that, it's about 7.76 cycles. And even if you think the memory access to the SRAM, it has to be serialized, it's only give you one additional cycle. So the answer by any means, no matter how you calculate it, how you approximate it, it should be very close to 8. So the answer would be C. All right. So it looks like now we have a consensus that cache can help us to speed up the applications specifically, right? So remember that without cache, it was 69 cycles, and now it's only about 8 cycles per instruction. Still far away from what we want for an instruction, but it's a lot better, 8 times better, right? But if you look, so now cache is an idea that has been integrated all processor cores. And if you look at, if you use a program called CPU-Z on Windows, it will give you the spec of your processor. So like at my home, I have a Ryzen 7, and then the Ryzen 7 would, it will show you that, my cache is like this. I have L1, data cache, L1, level 2 cache, level 3 cache. Wait, what are those, right? Why do I have multi-level cache? And if you see, and it's not just like, the anomaly of, AMD is not the only anomaly. If you look at the Intel Core i7, right, then it also have like 3 levels of cache, right? And each level of cache, they will have some terms that you will learn later. But now, why are we having these multiple level caches? So now I'm going to let you practice again for this question to see why deeper memory hierarchy can help in performance. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I think it's also a good time for you guys to chat with your friend for another 1 or 2 minutes to sync up the answers before we go into the whole classroom discussion. So now pull up the file that I put in a group chat and go ahead. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now according to your vote, we have an answer that's get 82% of approval rate. And right now I want to invite the team to tell us why you think that is the answer. So Team Instinct, can you share your thoughts with us? Who is the scriber of your team? Who is the scriber? Who is the scriber? Scriber of Instinct. We have quite a few of you, right? We have who in team one wants to share your thoughts? Okay, so Peng Fei.
Hi. I choose the choose the B.
Okay, your group chose B. Why?
Well,
because I said it's better, and you don't think it's better that much, so you chose B.
yeah, I think the result is closer to 4, rather than.
Okay, so how do you get your result?
So the so the first level with the latency of 0.0 nanoseconds is the one CPU cycle.
Okay,
so
this is one cycle.
Yeah, and for the second level, it's about 10 cycle.
10 cycle.
Yeah, so it's similar to the previous question. So first.
Okay, so how do you form the formula? Oh, by the way, formation. The formation of the formula really matters. If you don't follow the convention, if you don't explain why you have this formula perfectly, you are not going to score anything in your assignment and your midterm. So so that's why we have the assignment, right? So in the first assignment, a lot of you will probably get deducted because you don't explain how you come up with each number carefully. So that's why every time when we have the discussion, I want to make sure that you know where the number comes up. Okay, so.
Yeah, and for it's similar to the previous question. So first level is 1, and we put 1 here, and 1 add 10% multiply by. Yeah, so the 10%.
Okay, so this one is actually when everything is perfect, right?
Yes.
And we have 10%, and where the 10% come from is actually 1 minus 90%, right?
Yes.
And
it's multiplied by bracket by 10 plus 10 is the perfect perfect.
It's the
situation.
L2, right? The latency, if we can find it in L2, right?
Yes, and for the for the missed condition, we have 1 minus 60%.
Okay, 1 minus 60%.
Yes.
Times.
Times is similar. 52. 52 is the best. Is the worst condition. Yeah.
Okay.
And 52. Also 52 includes the 30% of low. Oh, we need.
Okay. So what if what if the 30% of the load, can they get also hit in the L1 cache and L2 cache?
Oh, let me see.
Right. So here you are missing one thing, right? So this is, you can assume this is the instruction part. So this is the instruction part. right?
Yes.
But
Yes.
for the data part, right, we also have 30% times 1 minus 90%, right, times 10 plus 1 minus 60 times 52, right? So
Yes.
that will be the final answer. Right. So if you look
Oh,
at
yeah.
that, right, that will be close to 5 cycles.
Oh, yeah. Yes. Yes.
Right. Okay, so I know this is a little bit complicated. I know it's time constraint, but you know, we want you to experience that so that when you are doing your exam or your assignment has more time, you will get a rough idea. But thanks, I think your answer is great enough for your team to score 1 point. All right, thanks. And now let's talk about, so now you know why processors has multi-level of memory hierarchy, even though it seems like the additional level of memory hierarchy has longer latency, smaller hit rate, right? But we still embrace the idea of having more hierarchy in your processor because it still helps us to improve the performance, right? So remember, we were starting from 69 and now we're down to 8 and now we are at 5, right? So a very, very significant improvement as long as you keep adding SRAM caches inside your processor, right? So if you look at the configuration of your processor right now, right? Like level 3 of the Ryzen, they have 8 megabyte of cache, and for level 2, well, 2 times 8 megabyte is about like 16 megabyte, and for level 2 they have 8 times 512 is like 4 megabytes, right? So it's getting larger and larger, and for Intel it's 12 megabytes as well, right? So they even though like their latency is long, but they still think it's a good idea. So if you look at the memory hierarchy now, this is just a simplified concept that between the processor and DRAM we have SRAM cache. But what the SRAM cache looks like right now is that the SRAM cache part also have different levels, and the L1 cache is the fastest but also the smallest, but the L3 is the slowest but also the largest in the SRAM memory hierarchy. But one thing to remember that all of them have to be faster than the DRAM, otherwise it's useless. Right, so that's the memory hierarchy. So now, one thing that you might want to question me is that, okay, professor, all you said, the math would work if the hit rate, as you mentioned, is about like 90%, 60%. But is that really the case? So now we have to explain why adding small SRAMs would make it work. And the reason is because we have locality. And from the textbook reading, you know there are some kind of locality, but I want to make sure that you know where the localities are from. So why don't you go ahead and practice question for about 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, looks like the answer is tied up on C and E. So it's a very good case why we should go into discussion. So go ahead and discuss, and the question is already in a group chat. Go ahead. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the discussion, wow, almost all C's are convinced by E's. So can I have, so let's see what team should we have the discussion lead today. Okay, Mystics again, can you share your thoughts with us? Okay, first of all, Joshua, do you have a question? Hello? Hello, Joshua?
No, I was just on team 2, so I was volunteering to speak.
Oh, okay. So you are the other scriber of team 2 today. Okay, what do you guys think?
So we did think it was E. So for spatial locality, we thought both sum and A are going to express spatial locality because in some
Okay,
case,
so first of all, what is spatial locality?
So spatial locality is the idea that data that's accessed, you're going to access data that's near it in space. So if I access the first element of a row in RAM, I'm likely to access the next and the next and the next. So doing kind of sequential accesses. And then, so they both express that pattern. Sum is only looking at the first 10 elements, but it's looking at them and they're right next to each other.
Right. So because every time when I access sum 0 and the next time it must be sum 1 and etc. until I reach sum 9, right?
Yeah. And in the same
way. And how
way,
about the AFI? Yeah, it's also the same way, right? From A0 all the way to A10,000, right?
Yeah. And for
Okay, so both of them have spatial locality. And what is temporal locality?
So temporal locality is a different notion which says that items that I access, I'm likely to access again soon, so in time. And some expresses temporal locality because we're just accessing those 10 elements, and I'm just looping over and accessing them again and again. So in time, I'm likely to keep accessing those same elements.
Right. So, okay, great answer. Right. So, and thanks for your contribution, and thanks for team two. You got the answer right, and a lot of you also got the answer right. I know. So, I think the explanation is perfect in a way that if you look at the definition of spatial locality, right, then A demonstrate perfectly on spatial locality, and like some also demonstrate spatial locality in a limited degree between sum 0 to sum 9, but it also have temporal locality because we are reusing this data. And some of you might think, oh, professor, you're creating a code that I would never write. Well, I guess you probably never write code like this. Well, sometimes you will. But thinking about most of the algorithms, especially those algorithms with table lookup, for example, dynamic programming, right? So it also has this kind of pattern, but just in different level of the nested loop. So in this way, you will figure out that a lot of algorithms, they do exhibit both temporal and spatial locality, right? So that's the data access part. And however, if it's not just the data access part, thinking about your code, right? So most of the time, if I am finishing a statement or an instruction, I would naturally go to the next one, right? Then this is spatial locality. And in our code, we like to have loops because we want to reuse the same pieces of instructions again and again. So the code itself also have the spatial and the temporal locality. So the answer is that both your code and your data have spatial and temporal locality. So most of the time, your program is just visiting a very small window of data instructions within a given period of time. So that's why it seems like you have a big program, but most of the time we are just using a small part of it in a period of time and gradually shift it to the rest part of the program. So because of that, right, most of the time you are just focusing on a small part of your data and instructions. So that's why the idea of SRAM cache would work. So the whole rationale behind the SRAM cache is that your program has locality. We are able to add just small pieces of fast memory to assist the execution of your program. But now, how to architect this cache to make your memory hierarchy, or say the cache design, more efficient to achieve better performance? That's the topic that we are going to talk about now. So the basic idea of this, right? So thinking about that, I have instruction like load store, and most of the time, if I'm loading an address, I am just loading a word. And if without cache, right, I need to get the word from the memory, right? And if I want to load the next word, if I don't have cache, I have to interact with memory again. So that's why every time when you are loading stuff, you have to pay this like a 69 cycle or 52 cycle overhead in accessing the DRAM. So now with the SRAM cache, saying that I'm loading a word, right, from the same address, and well, the first time, and the basic idea of cache is that, first of all, we want to capture the spatial locality. So the memory hierarchy, or say the cache design, we virtually, logically partition memory space into blocks. And usually a block, you can consider it as a consecutive memory addresses with their content in each of the logical block. So we partition the whole memory space as blocks. And whenever I want to load a data, saying that here right now I'm loading like this address. And in the very beginning, you can assume your SRAM cache won't have anything. So the first time when I load this data, it must not be in the SRAM cache. So instead of just loading the word with address 0x0020 in there, we load the block that contains this address. So every time when you need something, but that's not in the cache, we just load the whole block. And because you have the whole block in the cache, right? So although the first time we still have to access the DRAM to get the AABB from this block. However, the next time, if I am accessing an address like this 0024, because it's right next to where we just loaded the data from. So it's already in a block that's already presented in your SRAM. So this time we don't have to get the data from the SRAM. So the first optimization in our cache architecture is that instead of organizing the cache by word, we organizing the cache by blocks, and each block is a logically partitioned in your memory space that contains consecutive memory addresses and their contents. So that's why our cache is organized as a block, and whenever there is a miss, we getting stuff in the unit of a block. And whenever we want to manage the cache space, it's all in the unit of a cache block. So that's the first concept you have to remember. Caches are organized in blocks. So now the second question is that I have a few blocks in a cache. How do I know if the stuff that I want is indeed in the cache? So saying that I have a cache with content like this, right? And this cache, as you can see, it has 16 blocks. And how do I know what this 16 blocks stands for? So first of all, right, each block, as we mentioned, it stores consecutive content, right? So you can assume if I have a block that is 16 byte wide, then the first byte in a block must start with offset 0, and then because the next one is 1 byte away from the first one, so it's incremented by 1 until the end of the block. So so a block, they all have the same prefix, but the last part of the offset, or say the place in, it's just represent the relative position of the data in the block. And now, how do I know who is it, right? So you know all of them has the same prefix, right? So then you just put a tag associated with the block. So you will know that for this block, everyone start with this, and they have different offset. So this guy is all zeros, and this guy is 000F, because this is 00F, right? So that's so in your cache, you have to contain a tag field that records the prefix that is the common part of the address in the cache block. And in this way, so we call this prefix as tag field in your cache. Whenever I want to access the data, right? So your cache, you should accept that there is a tag array here. So saying that for this address, for this particular byte in the cache, right? This is going to be F078, right? So now, saying that, in addition to that, if you look at your cache design, there are actually more bits than just tag and data. So for example, there is a valid bit to tell if the data here in the block is trustworthy, because if you learn operating system, there is something like context switch, and in context switch, some of the data must be invalidated. And if you learn multiple parallel processing, you know that sometimes your data may also be invalidated because other processors are using it or are modifying it. So that's why you need a valid bit to indicate if the data here is trustworthy, is convincing or not. And there are also 30 bits to indicate if the data has been modified. All right, So that's the basic cache organization. And now, given this cache organization, if I am requesting an address like 0008, then this is a low-word instruction. And if you don't know what low-word instruction, it definitely means that you didn't do your reading carefully. Is the instruction that loads a word, and a word in the RISC-V architecture as we use in the textbook is a 4-byte. So what it tells you is that the load instruction will get 4 bytes of data starting from the address that has been specified. And this address must be word aligned. So its offset is always the multiply of 4. So saying that I'm loading an address 0x0008, then we have to look up the cache, and we know because we have 16 bytes of data within each block. So the block offset is always 4 bits. And because this is a hex decimal number, so each digit will represent 4 bits. So the last digit in a hex number is the block offset, and which represent this part. And the tag would be the remaining bits like 000. So I go through my cache and I will figure out that, well, this is the intersection of the data that I'm looking for, right? This part is the data that I'm looking for because I found 00 here, and this is the 4 bytes starting from 8. So what I will do is that I will return the data to the processor like this, and the processor will get CS space 2. Now, if I'm looking for another data like this 4048, again, I split the block offset because it's not in a tag. And now I'm looking for the cache, but I go through there. There is nothing called 404, right? So in this way, it means that the data that you're looking for is just not in the cache. So you should go to the lower level memory hierarchy in this way. So that's how cache works. Okay. But now you may have a question. When I search this tag array, right, it seems like I have to spend linear time to search for it. Well, linear time order n if you have a coding interview, and if you have an algorithm of order n, well, most of the time those software companies are happy. But you know, the cache can grow big, right? Like we said, the last level cache, they could have megabytes, right? And even now for the first level cache, we have 32 kilobytes. So you have kilos, thousands of entries to search. And when you search, you have to compare as well, and each will take cycles. So it's very expensive, right? So hardware people, actually, we also care about algorithm. And if you are familiar with the algorithm, you know there is a better algorithm that can, or data structure can help us search things faster. That is hash, right? And with hash, you can do it with order 1. So the real cache architecture, we actually make it a hash-like structure. So how to make that like a hash-like structure? So again, we still have data with like 16 byte. However, in your memory address, we select part of the address as the hash, as the hash result. So for example, this cache, I have 16 blocks. So it needs 4 bits to identify the 16 hash entries. So, so I select 1 more bit from its address as the hash result. And whenever I have an input, I just use the hash to specify, okay, if I want to have this data in a cache, it must, again, it must go into that block. So for this example, because the hash index is 0, so it will go to the zeros block in a cache. So in this way, you look at this. It's going to be 00 because the hashtag is the hash index is no more part of the address. It's used as the hash, and everyone go into that block should have the same hash value. So that could be ignored to save your space overhead. So in this way, I know as long as I see tag 00 in here, that's the data that I'm looking for. And again, if I have an address like 4048, right? Again, I partition the last bit as the block offset, and the hash index here is 4. So I go to 0, 1, 2, 3, 4, and because if the data is in the cache, it must be in the 4th index. And the tag here is only 31. It's 31, not 40. So again, 40 is not found. So this is a mess, right? So this is how, and in this way, you can figure out that every time when I search for the tag, I only need to visit one block. So it's an order one algorithm, and it's very fast. So that's, but a lot of you might also learn in data structure and algorithm that the biggest issue with hash is collision. So that's why most of the cache right now is a weight associativity cache, because in hardware, we cannot do like a linked list to create, to avoid collision. So instead, we just add a few more entries associated with each index. So now, given that we have a cache that only contains 16 blocks, if we make it a two-way cache, it means that each hash index would be associated with 2 different blocks. So so we just put the left. So each of this is the same index. So like this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So whenever you receive an address, right, and each and the blocks with the same hash index is called a set. So whenever you receive an address, we translate that into the binary number. And again, because this is a 16-byte block, so the last 4 bit should be used as the block offset. So we know this, and because we have 8 sets, or say 8 different hash indexes right now. So we need 3 bits for the set index, and the remaining part will be the tag. So for this cache, if I want to see if the data that I want is in the cache or not, first of all, with the block offset, I know if the data exists in the cache, it must be in this position. And with the set index, I know because this value represents 2, so I should go to the second set. And so I only need to compare if someone is code A1 or someone is code 01. 10. And if you look at this number, right? So this is actually 10. So then, and the left-hand side contains the data I want. So this side is a hit. So I would use a mux to select the output from this side as the data that I want to return to the processor. So that's how weight associativity cache works. All right. So it's very confusing here, right? I know this is how you feel. Like, first of all, how do I know how many bits do I need in a block offset? How many bits I need in a set index? How many bits I know I need in a tag? So here I give you Hongwei's first law on cache. You probably won't learn this somewhere else. If some people tell you this, it must learn from me. I'm not kidding. I believe I am really the first person who invented this equation. So this equation is called C equal to ABS. For those of you who are young, you are probably not experiencing the era that your car doesn't have an ABS in your system. But right now, if you draw, well, and in California, you're lucky enough. But if you have ever been in the East Coast where the snow might come by, when you drive in the snow, if you didn't control your car carefully, then this code anti-blocking system would help you get traction from your car. So your car should have ABS. That's the slogan I put for this formula. But what really is that the C here, so the formula is C equal to ABS, and the C here is the capacity of your cache in data array, and the A is the weight associativity of your data. And the B is the block size of, or say the cache line size, because the textbooks sometimes use the cache lines and of each block in your cache. And the S is the number of sets in your cache. So there are some other numbers, like if you have a direct map cache, then the direct map cache, it simply means that associated with each hash index, there's just one block. So that's one. And if you have a fully associativity cache, it means that your cache block can go anyway. So it's simply equivalent to one set. So these are the two spatial cases you have to memorize. Other than that, just put C equal to ABS into your in your formula, then you will find that. So and there are some corollaries of that. Right, so for the number of bits in your block offset is actually the log of your block size, because that's what we need to give address to each different byte in your memory data. And the number of bits in set index is related to the number of sets you have, and the remaining bits in your address will be your address, the remain part of your address. And usually, if you have a 32-bit machine and the address length is 32, if you have a 64-bit machine, then you can assume it's 64 bits. All right, so that's it. So now I want you to practice the C equal to ABS with this AMD processor real quick for 90 seconds. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so the answer looks very chaotic at this moment. So it's a good chance for all of us to open the file that I just sent out and start a group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at your discussion answer. Then it looks like we are now separated again into A and D. So can I have, okay, which group? Oh, mistake again? Okay, let's do it. Instinct again. Okay, we have instinct again. Okay, Valor, can you share your thoughts with us? Who is the scriber of today? Who is the scriber of today? Who is the scriber of today in your team? Valor? Someone in team 3, can you share your thoughts with us? Okay, now other teams, anyone? Open to public. Okay, oh now, wow. Okay, I saw Gotham, you are the first. Which team are you?
I'm from Instinct 1.
Okay, what do you think?
So I think the option A is correct. Tag is 49 bits.
Okay, how do you derive that?
Okay, previously you gave us the formula that C equals ABS, right?
Okay, C equal to ABS. What's the C here?
C is 64 kilobits here, 64 KB.
Okay, 64 kilobyte.
Yeah,
right?
sorry. And since it's a two-way set associated tree, you take A as 2 and the block size is 64.
Mm-hmm.
So
Mm-hmm.
therein you can get the value of S as 512.
Right, so this would give you an S equal to 512, right?
Yeah. And
so this is definitely not right.
No, I haven't been. Yeah, that is fine. I mean, I'm not done with the explanation, so just a minute.
Okay.
So after this, to find the number of bits in the tag, we have this formula of the address minus log of the number of bits in set index minus log of the number of bits in block offset.
Mm-hmm.
So number of bits in index would be log s, which is log 512, which is 9.
Mm-hmm.
And number of bits in offset would be log 64, which is 6.
Mm-hmm.
So to calculate this tag, it will be 64 minus log 512, which is 9, minus 6. So that would be 49. So here we directly have that index is 9 bits. So offset also is 6 bits. So option B and C are eliminated there. And since I got the tag is 49 bits, I just directly went with that.
Okay, great, right? So if you use C equal to ABS, it's not too difficult to have you derive this answer. And thanks for your Golan, your contribution. And if you still cannot get it, we will put the slides and you can review the lecture today. I know memory hierarchy is usually the worst. The part in undergrad architecture has the worst learning outcome. So I totally understand you probably didn't get it, but definitely make sure that you go back and look over the slides again. And before you leave the classroom, there are a few things that I want to mention. So first of all, assignment 1 due tonight, and reading quiz, there's one due this Wednesday before the lecture. And next Monday, we are not going to have a live lecture because my personal conflict, but I want to tell you is that next Monday, I will host a speaker called Joe Emmer. And if you don't know who he is a very, very famous architect, and he's going to talk a lot about the future architecture. And he's right now worked for NVIDIA Research and previously in Intel. So he will give you a lot of insight regarding what's going on. And there will be, it will start from 11 a.m. And so to encourage you attend that talk, I'm not going to have the lecture on next Monday, but do make sure that you spare your time. And if you can capture a screenshot, sending it through iLearn, showing that you attend a talk, you will receive a full credit reading quiz. And again, I will have an office hour tonight on Zoom. So if you have a question, feel free to come by. Other than that, if you have any other question, feel free to pass it on Piazza because we are running out of time. And enjoy the rest of the day. Goodbye.
Echoes of drinks bring back all the memories, and the memories bring back your.